Welcome to our next unit on transformations. Today we're going to see a brief overview of all the transformations that we're going to touch on, and we're going to focus in today specifically on a transformation called a translation. On your cover page for this unit, at the bottom, we're just going to be talking about T1, I can perform or describe a translation of a geometric figure. So translation in this sense doesn't have to do with language, it has to do with moving an object's position. We'll see more of that in a moment. The notation for transformations in general takes us from a point, which will be our pre-image, and it transforms it into a new point, which we're going to call the image. So this original one is called the pre-image, and after the transformation, it is called the image. And we denote that using this little dash mark after the letter, which we're going to read out loud as prime. So A transforms into A prime. So prime is how we're going to read that little dash mark. So in this picture here, quadrilateral ABCD transforms into A prime, B prime, C prime, D prime. And this is the type of transformation that we're going to touch on today, called a translation, which is simply moving every part of the figure to a new location. So every point slides the same distance and direction. Every point slides the same distance and direction. So this type of transformation falls into a category of transformations called isometries or congruence transformations, where the size and shape of the figure is maintained. Okay. Size and shape of the figure is maintained. The image and pre-image will be congruent. Another type of transformation we're going to encounter, but not specifically today, are similarity transformations. And this is where the shape of the figure is retained, but the size changes. The size changes. So in each of these, the figure that we end up with, in the case of a similarity transformation, we create a similar figure, creates a similar figure, where with a congruence transformation or an isometry, it creates a congruent figure. So a translation, where every point slides the same distance and direction, like in our example up here, everything stays the same spacing apart. A is the same distance from B as A prime is from B prime. D is the same distance from C as D prime is from C prime, etc. Now, with each of these, I'm going to put another example here using maybe a different shape. So it's more clear that when we perform a translation, the orientation is not changed. So when this slides over here, we have a shape that's the same size, same shape, it's just moved. Okay, so this is a translation. I'm going to briefly define the other transformations, but we're going to do a deep dive on those in future sections. We're going to focus mostly today on translations. But a reflection, we're just going to give us some definitions here. Reflection produces a mirror image, as you might suspect. Reflection, mirror image of a figure by flipping it over a line. This line is called the reflection line. So using that same image from that last example, that same pre-image rather, if I were to reflect that over this line, I would get a mirror image the same distance and same size. It's just backwards. Okay, so it gets flipped over. And my drawing wasn't perfect, but I hope you can tell this is just flipped over that mirror line, kind of like when you look at your reflection in a mirror, you see yourself backwards. A rotation, just like what it sounds like, we're turning the image to create a new one. A rotation, a figure is turned around a point to create a congruent one. A figure is turned around a point to create the image. So for instance, using that same L shape from the other examples, if I'm going to turn that around, say, this point here, to create this image, we're going to think of it like a bicycle wheel. Imagine I'm turning the spokes a certain degree measure, and everything about this gets turned. So this is let's see, it's hard to image. There we go. Okay, so it gets rotated a certain degree measure, and we have an identical image. Well, it would be identical if I could draw. Everything is rotated. So it's not flipped like in the reflection. It's just a rotation. If you were to turn your paper, you'd see the same picture as the pre-image. And then our last one, a dilation. This is like when you get your eyes dilated at the eye doctor. A dilation is an enlargement or a shrink, but it changes the size. So this is the only one of our transformations that is a similarity transformation. The rest are isometries. Changes the size of a figure, but not its shape. So keep the same shape, but not the same size. It could be an enlargement or a reduction. Enlargement or a reduction. So for instance, that same kind of L shape, if I were to blow that up, making it larger, that's an enlargement. Oftentimes we're going to enlarge from a point. We're going to enlarge from a point, kind of like we have a rotation point that we rotate around. An enlargement point, it's a point that we're enlarging or shrinking away from or towards. Notice how I can connect those points down here and make a little small L as well. Okay. So today's topic, so those are our transformations that we're going to have to work with. We're going to focus in on some examples of translations. So let's see some examples. So turn the page. So each point of a figure is moved the same distance and in the same direction. Just like from the previous page. Each point of a figure is moved the same distance and in the same direction. The notation that we're going to use to perform that transformation looks like this. We have a set of coordinates, x, y ordered pairs. They're being transformed so that we are adding or subtracting something to x, and we're adding or subtracting something to y to get us a new location, a new coordinate. An alternate way to describe this is using what's called a vector. The T stands for translation, and then these angle brackets indicate that we're moving that number A to the right and B, that number up. If A or B is negative, that just goes in the opposite direction, kind of like we're subtracting instead of adding here. So these angle brackets signify that this is not a coordinate, this is a movement. So this xy ordered pair, every xy ordered pair that we're given here gets transformed into this x, y minus 3. So notice there's nothing being added or subtracted to x, so that means all the x values of these are going to stay the same. So a prime is going to be located at 2, and b prime is going to be located at 3 still, and c prime is going to be located at 1 still for the x's. So all the same x's, all those same x values, 2, 3, and 1. And then for their y values, I'm going to take away 3 from each of these y values. So take away 3 from 3 to get 0. Take away 3 from 1 to get negative 2. And take away 3 from 2 to get negative 1. So graphically, what I'm going to do to A, B, and C here, y is the vertical position, up and down. So everything is going to get moved down 3 units. So from B here, I get moved down 1, 2, 3. Keeps the same x value, gets moved down 3. For C, keeps the same x value, gets moved down 1, 2, 3. And A, same x value, gets moved down 1, 2, 3. So this is now C prime, this is now B prime, and this is now A prime. And we connect the dots. Notice I don't have to transform all the in-between points. I only have to transform the vertices, and we find the new location of those. And when we connect the dots, we get the same shape. We fill in all the other in-between points. Okay. In the second example, this is given to us in the vector transformation notation, but it means the same thing. The first number is how far we're moving left or right. In this case, it's positive, so we're going to the right. And this 2 is our y difference, our y change. So up and down, we're going to move up 2. So we're going to have an m prime, an a prime, a t prime, and an h prime. And we're going to find their coordinates by adding those numbers to the coordinates. So we're going to add negative 5 plus 4 is a negative 1. Negative 2 plus 4 is a 2. Negative 2 plus 4 is a 2. And negative 5 plus 4 is a negative 1. Then we'll do the same thing to the y's. Negative 3 plus 2 is negative 1. Negative 3 plus 2, negative 1. Negative 5 plus 2 is negative 3. And negative 5 plus 2, negative 3. So graphically, each of these points, when I plot negative 1, 1, or negative 1, negative 1, 1, 2, 3, or negative 1, negative 1, there's m. When I graph a prime at 2, negative 1, and when I graph t at 2, negative 3, 1, 2, 3, and when I graph h at negative 1, negative 1, 2, 3. Connect the dots. So here is m prime, a prime, t prime, and h prime. Notice that the distance that they had to move from m to m prime, I had to go 4 units to the right and 2 units up. So 1, 2, 3, 4, 1, 2. Do the same thing for A. 1, 2, 3, 4, 1, 2. For T, 1, 2, 3, 4, 1, 2. for h 1, 2, 3, 4, 1, 2. We can describe that by the motion and by these new coordinates that we have. So our properties for translations, as we said on the front, a translation is a congruence transformation. So the pre-image and image are congruent, and all of the corresponding angles, notice how these are all right angles, these are all right angles. That angle there at A looks like it's the same angle there, that same angle there at B, same angle here. All the corresponding angles are congruent. And all the corresponding sides are congruent. So that word corresponding, just like when we were talking about the angles formed by a transversal on parallel lines, corresponding angles have the same relative position. So when we talk about angle M, we're talking about angle M here. M prime is the corresponding angle on the image. So these last two examples I would like you to do for class. We'll do those. We'll go through those at the beginning of class when we meet next. Sound good? I'll talk to you then.